Okay. You get the start of it anyway.
All right. Good afternoon, everybody. Welcome to Colloquium. This is, I've gotten used to, for Colloquium, kind of reaching out to people, some of whom I don't know, but often it's like through something I know, or whether I know somebody at the university or something. But today, today's speaker was a little different. So when the most recent Mersenne, next largest Mersenne prime was discovered, I happened to look at the press release, and I happened to notice that, actually at first I didn't notice, I just skimmed right over where the story was coming from, and then when I reread it a second time, I saw that it was coming from Blowing Rock. And as we all know, Blowing Rock is a hub of computational number theory. But now actually that I know what's going on in Blowing Rock, maybe it really is. But anyway, so I reached out to our speaker today, Mr. George Woltman, and said, hey, we'd love for you to come tell us about what all is going on over in Blowing Rock. The Western, we need a name for it, the Western North Carolina Center for Computational Number Theory, that's what we'll call it. Anyway, maybe that's not what he'll call it, but anyway.
Yeah, also known as my basement.
But anyway, we're excited today to have Mr. George Woltman, and with that, I'll let him get to it.
Well, first of all, I'd like to thank Dr. Morris for inviting me. It's a little bit of an honor here to be among you serious mathematicians. I am not one. You'll find that the hunt for prime numbers is more recreational than it is serious math. Anyway, with that said, well, let's get into it. A little bit of background about who I am. Like probably most of you, I grew up, just had a love for math and numbers, and particularly prime numbers, because they're just so easy to explain. Just as a simple refresher, it's a number that's divisible only by 1 in itself. 5 is a prime, 6 is not, because it's 2 times 3. Yet, even though they're so simple to describe, they appear so randomly. You'll find great regions where there are none, and then you'll find them several crammed together right next to each other. And it's led to several conjectures that are still unproven to this day. Like, are there an infinite number of primes just 2 apart? You'd think something that simple we might be able to prove by now, but as yet it has eluded us. Anyway, when I was really young, my dad brought home a letter with this postmark on it. And I was probably about 8 years old at the time. And I would be playing with prime numbers in the basement using an adding machine, or for you that are too young to remember, this was before phones had calculators, before electronic calculators, you actually had a mechanical adding machine. So I was probably playing with a 6-digit number trying to factor it, and these people came along and they found a 3,000-digit prime number. Well, if that isn't the most amazing thing in the world to an 8-year-old, like how on earth did they do that? So anyway, it kind of kept my interest in prime numbers going. Anyway, went on to MIT, became a graduate there, majored in computer programming and not mathematics. Sorry. Retired in 1995, and I needed a hobby. Wasn't very good at golf, so I thought, why not go back to that boyhood dream of looking for large prime numbers, and started to investigate whether this was going to be feasible. First of all, why would we go search for these large prime numbers? Well, the truth of the matter is, it really is just for fun. These mega-digit prime numbers have very little use today, or, well, virtually no use today. You can do encryption with a 4,000-bit key today. You probably don't need a 10 million bit key that probably would be overkill. Even if quantum computers come along and crack RSA, this is probably overkill for encryption. How about for the tradition of it? Some of the great mathematical minds of all time, Fermat and Euler, they were searching for large prime numbers. Following in their footsteps is hardly a bad thing to be doing. It is educational and motivational for young people out there. There are several times a year I'll get emails from young people excited about searching for prime numbers, and hopefully it'll spur them on to go on to more important endeavors in the field of mathematics. Other reasons one might search, just for the challenge of it. People climb Mount Everest for what to me seems like no good reason. I search for prime numbers to probably what them seems like no good reason. They're rare, and at least to mathematicians, they're probably beautiful. They have a certain elegance about them. There's massive numbers, only divisible by 1 in themselves. Just kind of amazing. For the more mundane reasons, people use it to test their hardware. It's very computationally intensive, and it can make sure your hardware's functioning properly. There is now actually some money you can win. Although if you're a real mathematician, you'll learn that the expected value is negative when you factor in the electricity costs and the cost of your computer. Also, some people do it to study the distribution of these Mersenne primes. We have a pretty good theory on how we expect them to be distributed, but a few more data points doesn't hurt to verify or at least raise questions as to whether that theory is valid. Going into the history a little bit, you'll find that throughout history, the largest prime number has almost always been a Mersenne prime. A Mersenne prime is 2 to the n minus 1. Not really good formatting there. There's the 1 over there. Mersenne was the person who kind of, he studied them, he gathered information from others who also studied them. He was kind of like the clearinghouse of his day for what was known about these numbers. Now, a Mersenne number like 5, these are the prime numbers known during his time. Like 5, 2 to the 5th minus 1 is like you take 5 2s, multiply them together, you get 32. Subtract 1 is 31, and that's a prime number. Even in his day, it was known that for 2 to the n minus 1 to be prime, n had to also be prime. So these were the known ones during his day. I think they also knew that 23 and 29 was not prime. So he made a bold claim. He came out and said, the next 4 are these. And that's all there is up to 257. 303 years later, we finally got the answer to his bold claim. He got 2 right, 2 wrong, and he missed 3. Not really a great track record, but anyway, these numbers are still named after him because he made this bold yet erroneous claim. Edward Lucas is the man who studied Lucas sequences, which was quite a breakthrough in number theory. That led to a test, a primality test for these large primes, Mersenne numbers, Mersenne primes. Before this, the only way to prove it was prime to go and try every factor up to the square root, see if you could find a factor. If you didn't, it was prime. If you found a factor, it wasn't. But his primality test was able to test the number without finding any factors, and it could do it rather quickly. In fact, in 1876, he found this 39-digit prime number, 2 to the 127 minus 1. And it'll probably be the record for all time of largest prime found with pencil and paper. At least if you claim to find one larger with pencil and paper, no one's going to believe you. Then came the age of the computers, and the records started to climb rather rapidly. In 1952, a fellow named Robinson, I believe UCLA, found 5 new primes in 1 year. Now we're up to 700 digits. The next 20 years, we climbed steadily, various people up to 7,000 digits. There's my favorite right in there. And then David Slawinski from Cray Research, or Cray Computers, he found the next 6, and we were up to 258,000 digits by the time I retired in 1995. So here I am in 1995 with this notion that I could go search for large prime numbers. Well, there's a couple problems. One, if you want to look for the next large prime, the exponent we were probably at is about 1 million. Slawinski was probably at about 1 million. So if we look for exponents between 1 and 2 million, we only need to test the prime exponents, but there's 70,000 of them. We expect to find a little under 2 Mersenne primes in that range between 1 and 2 million. And I have one whopping fast 0.09 gigahertz Pentium PC. And David Slawinski's out there with Cray supercomputers. But those are the problems, those are the challenges. But there are some possible solutions on the horizon. One, Windows 95 has just been released. Some of you are probably too young to remember it, but before that, your computer, if it was doing a word processing, it couldn't do anything else. With this preemptive multitasking, while you're sitting in a word processor, now you can actually have some program running in the background doing something useful, like searching for prime numbers. The other thing is the internet has just become known to the general public. So if I can rustle up 100 of my closest friends and like-minded geeks, maybe I can get a little help in my search. The other thing is Slawinski out at Cray Supercomputers. Supercomputer time isn't cheap. He's not running this program full time. As a matter of fact, what he's doing is whenever the Cray computer goes into diagnostics mode, that's when his program is run. So he's not making great progress all the time. Can we get rid of some of those 70,000 prime exponents between 1 and 2 million at relatively cheap cost? Well, the answer is yes. Back in Mersenne's day, we did know that all factors had to be of this form. So if p is 1 million, the factors are going to be possible factors are 2,000,001, 4,000,001, 6,000,001. So we don't have to search too many factors to, factor to a pretty good bit depth. And we can also eliminate half of those pretty cheap. A little too complicated to go into why that's true, but it's easily proved. And trial factoring nowadays eliminates about 63% of the candidates. Probably back in 95, I was eliminating maybe 55% of the candidates. So what that means is instead of having to test 70,000 exponents between 1 and 2 million, I probably need to test about 30,000 of those. So that's a big step forward. And this is Lucas's famous test. So simple. 3 steps to prove a number prime. You start out with a number 4. Why 4? Well, you've got to go study Lucas sequences if you want to figure out why you got to start with 4. There are other actual starting points, but 4 is the smallest one. You then take that, you square it, subtract 2, modulo the number you're trying to prove prime, and you do that p minus 2 times. If the result is 0, it's prime. So we can see that this isn't really a big math problem. This is a computation problem. That's my field. Here's an example, just to show you that it really does work. For p equals 7, you start with 4, you square, you mod, you square, you mod, you square, you mod, you come up with 0. That 2 to the 7th minus 1, which is 127, is therefore prime. Now, as far as how much work is involved, trust me when I say there's mod 127, you might think that's a division operation. Well, it's not. That's actually cheap. You'll find that every one of these numbers is a 7-bit number. You square a 7-bit number, you get a 14-bit number. If you take the top half, the top 7 bits, add them to the bottom 7 bits, you just did the modulo operation. So it's not division, it's really just addition. So the whole problem boils down to how fast can you do that multiplication? Well, to see if our quest is feasible, we need to see how fast we can multiply. Back in grade school, everybody learned how to multiply numbers. You calculate 8 times 4 times 3 times 2 times 1. That's 4 multiplications. 7 times 4 times 3 times 2 times 1. That's 4 more. To square or multiply 2 4-digit numbers, you're going to end up doing 16 multiplies. In computer terms, this is an order n squared operation, algorithm. What this does is this tells us how well an algorithm scales. It's going to cost, or the time it takes is going to be some constant times the number of digits squared. Thus, if we know it takes 10 seconds to square some number, if we double the size of the number, double the number of digits in that number, it's going to take 4 times longer to square that larger number. Well, going back to my PC that I had in 1995, how well is this going to perform? Largest known prime number is about 1 million bits that we're going to be testing. So we're going to need code that can test million-bit numbers or multiply million-bit numbers. A PC operates on 32 bits at a time. So a digit is really a 32-bit number, not base 10. So we want to multiply 31,250 digit numbers. That's 1 million over 32. Each 32-bit multiply is going to produce a 64-bit result. So we're going to need to do 1 multiply and at least 2 adds on the 32-bit halves. So we're going to need to do at least 3 operations for each multiply. And we plug that into our formula. There's our n squared, number of digits squared. 3 operations per digit divided by our computer speed, 29 seconds for each multiply. And we're going to need to do that Lucas test. We're going to need to do 1 million of those steps, 339 days. This is a bit of a problem. We need a better algorithm. Oh, and one other thing. Now, that's for a 1 million bit number. If we go to 2 million bits, we've got to do twice as many Lucas steps, and each multiply is going to take 4 times as long. So about 8 years to test a 2 million bit number. Next up, if you start nosing around on better ways to multiply, Karatsuba multiplication. If you're going to multiply a 2-digit number, AB times CD, you're going to need 4 products, AC, AD, BC, and BD. And you're going to end up adding AD and BC together. Just grammar school multiplication teaches you that. Well, you can calculate AD plus BC in a rather clever way. If you can do 3 multiplies, A times C, B times D, and A plus B times C plus D, which equals this, and then you subtract out AC, you subtract out BD, and you get this AD plus BC, which is exactly what we wanted. So it turns out, by doing some extra additions, well, several extra additions, we can get it down to 3 multiplications. And then if we do this recursively, we get our algorithm. So if we do an 8-digit multiply, we can break that into 3 4-digit multiplies. We can break down each of those 4-digit multiplies into 3 2-digit multiplies. So we're going to do 9 2-digit multiplies and 27 1-digit multiplies. Now you may note that A plus B or C plus D might overflow your definition of a digit, might generate a carry, but just ignore that as a problem for the clever programmer to solve. All right, so how does this one perform? Well, this is an order of n to the log 2 of 3, or n to the 1.565. That's better than n squared, but there's going to be a bigger constant of complexity in front of that. But we'll just estimate how long that's going to take. Let's just say it takes 7 operations instead of 3 operations it took before for the schoolboy multiplication. So we plug that into our formula. Our number of digits to that power times 7 operations divided by our computer speed, and we get 0.76 seconds. This is a pretty big improvement. And then we're going to do 1,000,000 of those Lucas steps, and it's going to take just 9 days. And if we want to test a 2,000,000 bit number, each multiplication will take 3 times as long. We're going to do twice as many Lucas steps. So a 2,000,000 bit number we could probably test in about 54 days. That's better. One caveat, though, is this really is a best case scenario. This number 7 here is probably quite optimistic. But we at least have an estimate of where we want to go. Can we do even better? Turns out we can. Fast Fourier transforms. If you learn one algorithm in college, I suggest it be the fast Fourier transform, because probably in the field you're going to go into that doesn't use fast Fourier transforms. And believe it or not, prime hunting and multiplication can use fast Fourier transforms. Basically what it does is it takes your number, takes log n steps to convert it into frequency space. You do this one point-wise multiplication in frequency space. You do another log n steps and come back to integer space, and you're done. And that's an order of n log n. The downside is it requires floating point arithmetic, which isn't accurate. Well, it's accurate, but you've got to be careful you don't lose too much bits off the bottom end. And you can only get about 9 bits in each digit. So now we're going to be dealing with much bigger numbers. Now each 1,000,000-bit number is really 111,000 digits. But if we plug that into our little formula here, we'd assume maybe 10 operations for each step. Divided by our speed, we get down to 0.19 seconds for each multiply, or 2 days. Now, if we go to a 2,000,000-bit number, each multiplication is going to take twice as long plus a little bit. This log n grows pretty slow, so 2 plus a little bit, and we'll do 2 times as many steps, or basically just 9 days to do a 2,000,000-bit test. So that's pretty good. We can do even better. In 1994, Richard Crandall and Barry Fagan published a paper on irrational-based discrete weighted transforms, or IBDWT. And it basically doubles the number of bits you can stuff in each digit. And even better, remember that modulo 2 to the p minus 1 step that I said was cheap? Well, it doesn't get any cheaper than absolutely free. Absolutely zero cost. So, I now can use my skills as a computer programmer, start writing a whole lot of assembly language code to get the most performance I can. And the actual implementation in 1995, late 1995, was about a day and a half to test a million-bit number. Going back to whether or not this quest is feasible, I get 100 computers, testing about 200 tests a year. I can get through those 30,000 exponents between 1 and 2 million in about a year and a half. So I think we've proved that this is a feasible quest. All right, so 1996, we launched the website for the Great Internet Mersenne Prime Search, or GIMS. Some people think that's an unfortunate name, but it was okay with me. This is one of the first distributed computer projects. Since then, you've had SETI and Folding at Home and several others. This was one of the first ones. Started in January 1996 with the goal to test as many numbers as we can. We would make all the results publicly available. We double check all our results. So we're going to do it right. In April, David Slawinski finds one more prime. That one. And it just so happens the day he sent me the email, I was testing that very same number about 6 hours away from completing it. Trends. That one hurt a little bit, but we carried on. By summer, we had our 100 users, had about 150 computers, not all as fast as we would like, but we're getting there. By fall, we had 700 people. Apparently more crazy math geeks like me than I thought there would be. And in November that year, we had our first success, 2 to the 1,398,269 minus 1. 420,000 digits. Turns out someone with some serious money made on the internet made an anonymous donation to the EFF, Electronic Frontier Foundation, to fund looking for these prime numbers, offering $50,000 if the first person to find a 1 million digit prime, $100,000 for a 10 million, $150,000 for a 100 million digit prime, and $250,000 for a billion digit prime. That kind of generates a little more interest. Prime 95, which was the name of the program that I created. Wish I hadn't called it 95. It kind of sounds a little dated now. It turns out that this is a great little program to test how good your hardware is and your memory, especially the floating point unit and your memory. Overclockers love it. They just ramp up their clock speed, run Prime 95, it fails in 5 seconds, and they dial it back. But it turns out Intel also uses it to find some flaws in their chips. For a while, they were using a small subset of the code to bin their chips, decide which ones could operate at which speeds. And over the years, it's found 2 chip flaws in chips that were actually in production. In 1999, found our first million-digit prime number. It actually had 2 million digits. In 2008, we found the first 10 million-digit prime number. That was found in UCLA. And where are we today? Since we found 17 Mersenne primes over the years. There's only 51 known. They're pretty rare, and we've been quite lucky to find 17 of them. We happened to start our search in a time when they were, rather than a desert, an area of abundance. The latest discovery that Professor Morris noticed was last December. 2 to the 82,589,933 minus 1, found by a fellow in Florida, 24.8 million digits long. Big enough to fill about 10 of these textbooks. So pretty big number. I could display the number of the digits here, about 1,000 a page, 1 a second. We'd probably be here for about another 7 hours. So it does take a while to comprehend the size of these numbers. Got about 6,500 users currently. There are 21,000 computers that have submitted results within the last year. Not everybody hangs around. People come and go, so it's not like I got 21,000 computers actively contributing every day, but it's probably more like 10, 15,000. We complete about 250 primality tests every day and 150 double checks every day. The reason we need to do double checks is not guaranteed that the first test worked without error. What we do is remember the last 64 bits of the last number in that Lucas sequence. And then we run the test again, and he sends in his last 64 bits, and if they match, we have a winner. If they don't match, we send it out and test it again. So we're pretty sure once we get a match that it really isn't prime. We're currently testing exponents around 90 million now. We've made some other improvements along the way. We currently look for factors using a P-1 factoring method, Pollard-Rowe. We actually don't use Lucas-Lamer testing anymore. Just a year or two ago, someone discovered a way to do a Fermat probable prime test, and the error checking on that is you're not going to complete that test without giving us an accurate result. The chance that you would have a hardware error corrupting your result is pretty darn near zero. We now use GPUs, graphics cards, to do all our trial factoring. They are great at it. They're just like thousands of little cores on this one little board, all just doing their trial factoring. So we've been improving along the way. And that's where we stand today. If there are any questions, or if you'd like me to go into more depth on anything, I'd be happy to do that.
So to check one now, about how long does it take?
I've got a computer at home that's probably about 3 generations old on Intel. And it takes about 8 days to test a single number. Yeah. Intel has really slowed down, though, on their rate of progress. Nowadays, the rate of speed is limited by how fast your memory is. The CPU core is actually running faster than the memory can keep up with. The fastest hardware right now is a Radeon 7 GPU, which they discontinued, unfortunately. And it can do about 2 tests a day. Yeah.
So are you like remodifying and distributing this code like on a regular basis to as you improve it for using different?
Yeah. Question was, is the software being improved on a regular basis? And the answer is yes. Every time Intel comes out with a new instruction set, SSE, SSE2, AVX, AVX2, AVX512, I've got to go rework all my assembly code to take advantage of the new instructions.
And then you send it out again.
And then it's, yeah. At Mersenne.org, you can download the software absolutely free. You can even look at the source code. It's all there except for one little bit. And that's just the thing that sends the checksum in to make sure people aren't hacking results and spamming me with bogus results. And if they really wanted to, they could work around that with some reverse engineering without too much trouble. So it's basically a trust-based system. Yep. Anything else?
Do you have so right now, do you have a computer running this thing? I mean, like, do you always have a computer running this in your house?
I have 16 CPUs running it all the time. And I got 4 of those graphics cards running it all the time.
How frequently are these, so I mean, does one machine run the full test and then report back to you?
Yeah.
Or is there an occasional check-in as this process is going?
When you fire up the program, it talks to a server. Back in the original days, you actually would send me an email and I'd send you a range of numbers to test. But doing it by email got a little cumbersome. We now have an automated server that does it. It'll talk to the server, and the server will send you one exponent to test. You test that all the way to completion, and you send back the last 64 bits of the result, and you're done. It's very low bandwidth. We don't try and send intermediate results. The bandwidth costs on the server would be pretty enormous for not a lot of gain. And when you submit your result, the server sends you another one to test.
So if, for example, somebody, starts up the program but doesn't run one full test to completion, I guess I wasn't sure if there was some, you just would never get you wouldn't even get like a partial result. You would just, it's lost in the ether.
Yep.
Kind of, yeah.
Wasted cycle.
And do they know which numbers their computers?
Yes,
it says like the
it tells you the number you're testing. It tells you the chance that it's going to be a new Mersenne prime. If you're lucky enough to find one, it beeps like crazy so that you know. We don't hide anything from you. You'll know when you found one. It turns out the biggest contributor right now is the University of Central Missouri. They've got all the computers in their campus running this software. And last I heard, it's about 850 computers, and he's found 4 of the 17 prime numbers. He must have a very, very nice boss there that lets him run up those huge electricity bills, because it's probably about $50, $60 in electricity per year per computer.
Or he just installed them on there. His boss doesn't know.
I don't think he did that. But he's gotten some publicity for the university, too. So, the other thing is, I talked about those awards the Electronic Frontier Foundation is giving out. Well, we claimed the last one for $100,000. And we broke it down, and we gave $3,000 to everyone who had found a Mersenne prime before the 100 million digit one, and save some money to give $3,000 to people who find it after the 100 million digits. So he's gotten $12,000 to help compensate for his, I don't know, $100,000 of electricity he spent. Yes?
So, what about the Radeon 7 makes that optimal for this one?
It's got high bandwidth memory on it. And the Radeon 7 has double precision floating point at 1/2 the single precision rate. The GPUs that NVIDIA sells, they sell the high-end GPUs for $5,000 a piece, and their double precision runs at just as fast as I think the single precision, or maybe at half the speed. When they sell the consumer cards, they cripple the double precision rate to about 1/32 of the single precision floating point rate. And that way they can sell that for $500 and the high-end card for $5,000. AMD does somewhat of the same, but for some reason on this one consumer card, they didn't cripple the double precision floating point rate. and they coupled it with high bandwidth memory, and the thing just flat out performs.
Would it be, like, if you could get your hands on a Titan, would that be better than the Radeon 7, or?
Radeon 7 will beat a Titan.
Interesting.
So is there an advantage from a computing perspective? Is there an advantage to this being distributed beyond the practical thing of, well, it's hard to get supercomputing time and very expensive? I mean, is there a real computing advantage to the distributed nature, or just that really allows you more cycles than UBD?
The distributed computing just gives you more cycles.
Okay.
If I were doing this alone, I'd probably wouldn't have gotten to 2 million yet. So I didn't always have 17 computers in my basement running.
Other questions for us?
Have you found any personally?
I have not found any personally. The closest I came was 6 hours away on the first one. That's okay.
Other questions?
Matter of fact, the last one that was found was his 4th test.
Wow.
I've probably done about 20,000, got no successes. He comes in and hits it on his 4th try.
It's like buying your first lottery ticket and it hit, you know.
Yeah, and the guy in front of you bought $500 worth and all losers, yeah.
Well, if there are no other questions, let's thank our speaker.
Thank you for having me.